Okay, so let's start with the first exercise. The first exercise tells us, assume that the following bodies have the form of a sphere and fall from resting there. A raindrop and a baseball. For each of the previous bodies, calculate the following quantities. So let's start with the raindrop. The raindrop has a diameter r of 2 millimeters. This is equivalent to 0.002 meters, and a mass density of 1,000 kilograms over meters cubic. So we have to get first the coefficient of the viscous term and the coefficient of the drag term. We know it by the next formulas, and this has two coefficients. These two coefficients they have already given by this. Okay, so next we plug in the values. After plugging in the values, we get K and D as the coefficient of the viscous term and the coefficient of the drag term. Then we have to get the critical velocity, and for which velocities does the term kv dominates, and for which velocities does the term dv squared dominates. So solving for v is going to give us the critical velocity, and it cannot be zero. So we solve for v, we pass v to the other side and divide by v squared, so we get this thing here, and solving for v is k over d equal v. So we plug in the values that we got previously, and we get critical velocity, and kv dominates for velocities that are lower or equal to 0.078 meters over second, and dv squared dominates for velocities that are over or equal to 1.78 meters over second. So the second problem tells us the terminal velocity v term. We have to make the sum of forces, that is here. This is the weight. This is the weight. Minus this is foot resistance. That is equal to 0, because we're gonna get the b, the velocity terminal velocity. So we have the density, but we need the mass. So we use a formula of the density, that is mass over volume equal to density, and we have to get the volume. We have already the radius, that is 0.002 meters. So we plug in the values in the formula of the volume, and we get the volume. Then we solve for mass, and this is the equation that we get, and then we plug in the values that we know, the density and the volume, and we get the mass. So now it's just plugging the values of this formula, of this one, and we get it like this. This is a mass times gravity minus the coefficient k minus the coefficient d. These are the viscous terms and the drag term respectively, and we get a quadratic equation. So we solve for the v's, and we get two terms. We cannot use the negative because we're using a positive direction of the weight. So this is the velocity that we get. Okay, so the third problem tells us, assuming no air resistance, the time it takes for the body to reach terminal velocity and the distance the body has traveled. During what time interval is the ideal motion, that is no air resistance, applicable? Okay, so we got this formula that it's for free fall, and we know that this is our v term, and this is our, and it starts from 0 because it starts with no velocity, and we want to get this because it's time, the total time. So we solve for t, and this is the formula that we get, and we plug in the values, and this is the total time that it's going to reach to get that terminal velocity. assuming there is no air resistance. Okay, so now let's start with the baseball. The baseball has a diameter R of 75 millimeters. This is equivalent to 0.075 meters. Then we're gonna use them to get the coefficient of the viscous term and the coefficient of the drag term. Here we need two other coefficients that are from the medium air resistance. We already have them here and here. So we plug in the diameter R, and we get two results. This is K and this is Z. Then the first problem tells us the critical velocity, for which velocities does the term kV dominates, and for which velocities does the term dv squared dominate. So we have this formula where b equal cannot be to 0, b cannot be 0, and we solve for b and we get k over d is equal to b. So we plug in k and d and we get this, that is our critical velocity. Then we know that kV dominates for velocities that are lower or equal to 4.7 times 10 to the negative 4, and dv squared dominates for velocities that are over or equal to 4.7 times 10 to the negative 2. Then the terminal velocity. Okay, so we know that our y-plane, the way is up downwards and the fluid resistance is upwards, and we're gonna choose our direction downwards, positive direction downwards. So this is the same as this. Then we plug in the values as the next formula. This is a mass, this is a gravity, this is a k coefficient, this is a d coefficient, and as we see it, it's a quadratic equation. So we solve for x and we get two values. We're gonna choose the positive one, that is this one, and this is our B terminal. It's 17.053 m over s. Terminal velocity and the distance the body has traveled during what time interval is the ideal motion, that is no resistance applicable. So this is what we want. Okay, so this is an equation for free fall to know the velocity, and we're gonna use this as our velocity terminal, or terminal velocity. And BOY, so it starts from rest and our initial velocity is 0. So we solve for t, we pass g to the other side, dividing, and we get this. So we plug in the values and we get 1.74 seconds.
For exercise 2, the first thing that we need to do is obtain an expression for the terminal velocity, given the formula mass times gravity minus the constant d times the velocity squared, and this is equal to 0. Here on the left, we can see that we have the weight, and here on the right we have the drag term. So the first thing that we need to do to obtain the terminal velocity is pass the drag term to the right. So now we have mass times gravity equals the drag term. Now we pass the constant d dividing to the left. So now we have the weight divided by the constant d, and this equals the velocity squared. Now we take the square root of everything that is on the left, and this gives us the formula for the terminal velocity. So let's say we have two objects with the same shape and size. They both share the same constant d, but the one in the left has a higher mass than the one in the right. So which one reaches a higher terminal velocity? By real-life experience, we already know that objects with higher mass reach higher velocities. But we can also prove this via the formula that we calculated on the previous paper, which is the terminal velocity equals the square root of the weight divided by the constant d. So since they both share the same constant d and gravity never changes, by augmenting the mass, we will also obtain a higher terminal velocity. So the one with the higher mass has a higher terminal velocity, thus would reach the surface faster than the one with the less mass. But let's take this to a more practical example. Here we have two guys falling through the air in a spread eagle position. They both share, like in the previous example, they both share the same constant d. For this example, the constant d is 0.3 kilograms per meter. But, like in the previous example, the one in the right has a mass of 100 kilograms, and the one from the left has a mass of 50 kilograms. So we already know that the one with the higher mass is going to reach a higher terminal velocity. But let's prove this by plugging in the values in the formula that we already have calculated. So we have v term is the square root of 50 kilograms times the gravity divided by the constant d, which is 0.3 kilograms per meter. This would give us a terminal velocity of 40.43 meters per second. Now, if we plug in the values for the one with the higher mass, we would obtain, that is the square root of 100 kilograms times the gravity divided by the constant d, which is 0.3, and this gives us a terminal velocity of 57.18. So here we can compare, and we can see that the one with the higher mass, the one with 100 kilograms, reaches a terminal velocity of 57.18 meters per second, while the one with the lower mass reaches a terminal velocity of 40.43 meters per second. Thanks.
Alright, so exercise 3. according to the vicious term. We're gonna neglect the drag term for this exercise, so we're left with mass times gravity minus vicious term times velocity terminal equals 0. Now, first we need to obtain an expression for the terminal velocity, which is v term, and so we solve for v term now, and we obtain mass times gravity divided by the vicious term equals to the terminal velocity. Now, if we have two objects with the same exact physical size and with the same vicious term, we can know which one's gonna fall faster than the other without even having to do the actual operation. And how is that? We can deduce it by knowing that gravity is the same for both objects, and the vicious term is the same for both objects. So if you multiply a big mass or a large mass by the gravity and then divide it by a vicious term, you're going to get a large velocity terminal. Now, if you multiply a smaller mass by the gravity, which is the same for both, as we said before, and then divide it by the same vicious term, the terminal velocity you're going to obtain is smaller than the first object because, well, the mass is smaller, hence the larger the object, the more velocity terminal it's going to have. So that's exercise 3. Alright, so experiment or exercise 4, which is actually an experiment. I'm going to explain how we did it, and later on in another video or another fraction of a video, I'm going to explain everything about the numbers and all of that. Right now I'm just going to go ahead and explain how we carried out the experiment and how we measured the times and the distance and position and all that stuff. Okay, so here we go. Okay, so we did the experiment 3 times, as you could see. We put a small marble right on the surface of water. Like, we filled a tube with water, with 40 centimeters of water, and we hold a marble right on the surface, and then we let it go, and we taped it. We have it on video, and then we used this app called Visual Physics, Vernier Visual Physics, to do what you are seeing right now in the picture. Like, with that app, we were able to map out point by point where the marble was, and so the app did all the analyzing for us, and it basically it just knew at what time or at what position the marble was at an exact time during the video. Like, the video is really short, you saw them, it's 1 second, so it's pretty difficult to just put a stopwatch beside the tube and see where the marble is at what time. So this app does just that. And we had to put the scale, and which was 0.4 meters downwards, of course, and the origin was the surface of the water. And so with all this data that we put in the video, like all the dots, all the little red dots, and the scale and the origin, the app was able to analyze the video and give us its precise position at any given time. Like, at the time where we put the dots, like, it measured at what time how much time had passed from one dot to another, and it automatically gave us the position of the marble with respect to that time, and it also gave us a graph of position versus time. So we were able to just extract that data from all three videos and do the average terminal velocity for the experiment. And basically the app does all the analyzing. Like, it makes it way easier than to have a stopwatch, so that simplified the process, and that's how we got the data. Alright, so on to the mathematical explanation of exercise 4, which is the experiment. You just saw another 1-second video of the experiment, of what we did. You already heard the explanation of how it works. So now I'm gonna show you how it mathematically works. So with the app Visual Physics, we obtained 3 different terminal velocities for each time we did the experiment. In order to obtain a terminal velocity, like a general terminal velocity, we did an average of the 3 of them. Now, by the way, the results are all in negative because, as you can see in the diagram I drew, we took positive movement upwards and positive to the right. So since it's going down, it's negative. So the first terminal velocity is, well, all terminal velocities are in meters per second. So the first one is minus 0.651, then minus 0.629, and then minus 0.641. That gives us a total average velocity terminal of minus 0.640 meters per second. Now, we measured the marble's mass, which turned out to be 5.5 grams, which we converted to kilograms, resulting in 0.0055 kilograms. Now, using the equation we deduced from the past exercise 3, we solved for k, and we plugged in the values in order to obtain k, right? So mass times gravity divided by velocity terminal gave us a k of minus 0.0842, which we then turned to positive because we're taking the absolute value of k, and it turned out to be 0.0842. Now, the teacher gave us this next equation, which is position at time t. What we did was we plugged in the values we already knew, and after after we had that done, we substituted the value of time with each of the values of time that the application gave us. As you can see in this table, the blue, the orange, and the gray are data from the video that's like automatically given by the app, and on the far left column you can see the times we used. So those times are the ones we substituted for t in the equation the teacher gave us, so we could obtain the yellow column, which is our theoretical position given time, right? So it's basically pretty close, like there's not too much of a difference, and but we're gonna see in the graph just about in a second. We're gonna see the graph how it behaves. There you can see all the blue, the orange, and the gray graphs for the applications analysis, and then the yellow one is for our own equation of position given any time. And as you can see, they are all pretty similar with each other, so we can conclude that the value of k that we obtained by our own means of calculations is a good value of k. It's a right value of k. The graphs are going downwards because, remember, we took positive upwards, and so we can say that our experiment was pretty accurate.